Hello, Principles of Biomedical Science students. Welcome to the video walkthrough of 1.1.6. Now I'm using Block 3A's Biomed class page as the example, but you'd be on your own page, right? Click from Stream over to Classwork, and you want to go to either Tuesday 10:13 if you're one of my 8A students, or it will be Thursday 10:15 if you're in Block 1B. So click open the lab journal and you're going to open that up and it's going to look like this, DNA analysis. Our goals for this particular section: create and analyze DNA profiles. We cannot create them, but we can analyze them. Perform gel electrophoresis and interpret results. We can't perform electrophoresis until we're back together at Horlick, but we will analyze some results. Practice precise and accurate micropipetting. Well, we cannot do that until we're back at Horlick. Okay, so you have this open. Next thing you want to do is log on to MyPLTW with your username and password, or if yours isn't working, general student and password 1. So you log on, click on courses, choose Principles of Biomedical Science, and then from the left side scroll bar, click on Lesson 1.1, Investigating the Scene, and scroll down to 1.1.6, DNA Analysis. All right, so here we are, today's lesson. Remember, last time we were together, we talked about how when you find DNA at a scene of crime, you have to make millions of copies of it with PCR. So you make copies, then you add a restriction enzyme, and that cuts DNA at specific sequences. And your DNA will cut into different fragments from the person living in the same house as you. So you have your DNA, you've made copies, you've added your restriction enzyme, and you've let it cut the DNA into pieces, restriction pieces. So you have your digestion here. So you have all these different little fragments now, and you need to see what that looks like. That's the DNA profile. And that's where gel electrophoresis comes in. If you look, guys, each column up and down in a gel is called a lane. The first lane on the gel I'm showing you here is called the ladder. We always run a ladder so we know what size the fragments are. The second lane shows 2 bands. The third also shows 2, but notice they're different from the second lane. The fourth lane shows 2 that are the same as the second lane. See how they're the same? The fifth lane shows 3 bands, which are different from all of them. The sixth is the same as the fourth and the second. And the seventh is the same as the third. Notice how they match up. And if you're curious, this is, I think, from when we diagnosed Anna Garcia's family with sickle cell in the old curriculum. It's just an example. So we're going to analyze samples of blood found at the scene on the table and the floor. And we're going to analyze Eric's DNA, Dominique's DNA, and Anna's DNA. So take a minute, think about why we're only doing those 3 people. So what reason did you come up with? What do all 3 of those people have in common? That's right, they're all type A blood. And since the blood we found at the crime scene we identified as type A, there's no need to test anybody who isn't type A. So the next question we need to answer, what are restriction fragment length polymorphisms? Ooh, fun to say, even more fun to learn about. So if we look, if we scroll down and down and down, here it is. Variations in DNA fragment sizes. So I'm going to type that. Variations in DNA fragment sizes that result from restriction enzymes cutting DNA at recognition sites. Right. So everybody has different restriction fragment length polymorphisms. Every person in the world. Maybe identical twins have the same. I'm not sure. I'd have to look that up. So here we're going to do some labeling. Take a minute now and think about the last time we were together. We said DNA has an overall what charge? Negative. That's right. And if DNA is negative, is it going to want to run towards a negative charge or a positive charge? Remember, opposites attract. So will it go from negative to negative or negative to positive? Positive, you're right. So here's where we load our DNA, and that's going to be negative. Okay, when we do this in class, you'll hook up electrodes and you make sure that the negative electrode is where we put the samples in. The positive is going to be down here. There we go. So you have your positive. I guarantee you guys, at some point in college, you'll probably hook your gel up wrong. And when you do that, the DNA is going to run right off the short end of the gel, and you'll come in on a Saturday and you'll make that up. So now we have to label all of the bands in sample 1, okay? It's just like a type of graphing. So if we look here, the check for understanding, this first band in sample 1 is between 1600 and 2000. See how it's between these two numbers? So let's look at our choices. Which one of these numbers down here is between 1600 and 2000? 1650. You're right. So let's label that. That's 1650. BP stands for base pairs. Now the next stripe, let's look at that. So here's the next stripe down. Notice the stripe here is sandwiched between this one and this one. So this second stripe is between 1100 and 1600. Let's look at our choices. Which one is between 1100 and 1600? 1300. Good job, you're getting this. 1300 base pairs is between 1100 and 1600. Next stripe. So we did this one and this one, now we're on this one. Take a look. This stripe falls between 800 and 1100. So this stripe is higher than 800 and lower than 1100. So let's look at our choices. Which one is higher than 800 but lower than 1100? 950. I think you've got this. Fourth stripe, let's take a look. See, this fourth stripe is higher than 600 and lower than 800. So look at our choices and find the number higher than 600, lower than 800. 650. Good job. And the last one, higher than 300, lower than 550, given your choices. Which one is above 300 and lower than 550? 400. You've got this. Perfect. We've labeled everything. Now we get to watch the videos. Enjoy the music for the videos.
Dilute your concentrated buffer to store the video as well. Refer to Table A for the specific amount referring to your casting tray size. Step 2. Mix the alcohol buffer solution with a 250 milliliters. Step 3. Dissolve the alcohol rolling the solution. Hold the alcohol to 60 degrees Celsius with careful swirling and continuous dissipation. Step 5. While the agarose is cooling, seal the ends of the gel casting tray with rubber end caps. Place the gel template on the appropriate edge. Step 6. Pour the cold agarose solution into the prepared gel casting tray. The gel should solidify within 20 minutes. The gel will stiffen and become less transparent as it solidifies. Step 7. Remove the end caps of the cone. Particularly, removing the cone and end caps to prevent damage to the gel. And now you have your gel prepared and ready for electrophoresis. Now continue to perform electrophoresis.
All right. So you probably won't prepare your own gel until you're either in college or maybe in biomedical innovations if you're in this pathway. But you will run your gel. So let's watch this one too. Enjoy the music.
Ecotech instruction videos performing electrophoresis. In this video, we'll demonstrate electrophoresis in easy steps. Watch our video preparing the agarose gel tray before starting this experiment. Step 1. Place the gel tray into the electrophoresis chamber. Completely submerge the gel with diluted electrophoresis buffer. Refer to Table B for recommended volumes. Step 2. Load 35 to 38 microliters of dry samples into wells in consecutive order, starting with the closest well. Step 3. Place the safety cover and check that the gel is properly oriented. Remember, the dye cycles will migrate toward the positive electrode. Step 4. Connect leads to the power source for electrophoresis. Refer to Table C for time and voltage guidelines. Here's a time lapse of our experiment sequence migrating. Step 5. After electrophoresis is complete, remove the gel and casting tray from the electrophoresis chamber and visualize the results. No staining is necessary. And here you see the results.
All right. In samples that we run, staining will be necessary. So we're going to watch this one too, because I know you love the music.
EdVerTech instructional videos. Visualizing DNA using CyberSafe stain. For this experiment, you will need an agarose gel with DNA samples, concentrated CyberSafe stain, diluted electrophoresis filter, a small tray or label, aluminum foil, your pipette and tips, and finally, the UV transilluminator. Step 1. Dilute the CyberSafe stain by adding 7.5 microliters of the concentrated stain to 75 ml of electrophoresis filter in a flask. Mix the solution well. Step 2. Remove the agarose gel from the casting tray from the electrophoresis chamber. Carefully slide the gel out of the casting tray into a small gel staining tray. Step 3. Submerge the gel in the diluted CyberSafe stain solution. Cover the tray with cooling and the gel from left. Stain the gel for 10 to 15 minutes. For best results, use an orbital shaker to gently agitate the gel while staining. Step 4. Remove the gel from the staining solution and visualize the results using the UV transilluminator. The DNA bands will appear red green against a dark background.
Pretty cool. All right, so let's go back to our lab journal. We watched the videos, yay. Here are the results from the crime scene. Here's the ladder, the blood from the table and the floor. And before we compare them, what do you notice about those two samples? That's right, they're the same. So you also have Eric, Dominique, and Anna. And doing the comparison, you'll see that these two match Anna. That's right. It's pretty easy to see. All right, it's Anna's blood. All right, so now forensic experts. I'm going to highlight this, this, and this. I'm going to bold it, and I'm going to put here, answer these before you submit this assignment. Those three things are what you're going to answer on your own. The rest we do together. All right. So currently a national database containing DNA profiles for everybody in the country does not exist. Each state has its own laws about when DNA is collected and how long they keep it. So think about this. Whether you support this or not, give me a reason why a national database could be useful. Yeah, most people say it'll help police or investigators solve crimes. And it would. What's one reason not to create a national database? Think about having your DNA in a national database. How would that make you feel? Yeah, right. It's invasive. Um, you probably want your privacy. That's what most people have been saying. All right, so the conclusion question. DNA evidence analysis is an imperfect science. What's two reasons why this may be the case? So let's stop and think about what we talked about yesterday. Can you be framed by your own DNA? Yes, you can. So it could be that DNA at the scene is not related to the crime. That's one reason this is imperfect. Another reason, picture the person running the DNA. It's a human being working in a lab. What do you know about human beings? Yeah, we make mistakes, so it could be human error in the lab. So there you go, guys. This is what we did together. We learned about electrophoresis. We will perform it when we meet back at Horlick. You need to do these 3 things I have highlighted. Thank you.